confused with what we're actually
No,
trying
no,
to
I was
prove.
thinking of the homework because the homework 0 was considered to be even.
Oh yeah, 0 is an even number.
Huh.
Because it's equal to 2 times 0, which is by definition even.
So it's 1 times 0.
Well, 1 times
That's
0.
not the definition of even.
1 is equal to 0 times 1 plus 1, which means it's odd. Oh. Oh, snap.
So we made some mistake on the,
So
on the
wait.
homework.
Plus 1.
Okay, even numbers, ready? -4, -2, 0, 2, 4, right? And it goes on forever. Okay, those are even numbers, right? Like you guys learned that way back in like 2nd or 3rd grade. Okay? Or hopefully you did. I don't know what they teach in Common Core anymore. -3, -1, 1, 3, 5, those are all odd numbers, right guys? So that's the definitions of even and odd, and you can make it fit these, okay? So does that help out any, or hopefully not erasing like, 20-some years of learned math? Oops, although that might not be a bad thing. Okay, so regardless, let's go back here, okay? So for all even integers, x to the 4th is in z, okay? It looks like it's true, right? We didn't find a counterexample, so let's start out by defining the x variable, okay? So this is, if I was to do this in steps, let's let x be an element of z even, okay? And in brackets, again, you don't have to put this, but x is arbitrary but particular. Okay. What's the only possible thing that we can do at this point with x? Yep, we can say x is equal to 2n for some integer n, right? That's all we can do because we've just defined x to be even. Okay? So, by definition of even, x is going to be equal to 2n, and I need one more thing there before we can conclude part 1.
X is, n is an element of z.
That's correct. Nice. Okay, so n is an element of the integers. Okay. Let's say you're on an exam and you forget that. That's a half point. Okay. On the homework, I might just write it in there the first time. Okay, but if you keep doing it over and over and over again, then I'll take off points because I don't like writing in right answers. Okay. All right. So that's part 1, right? We can all do that. Okay. Part 2. We need to start with what, guys? Rhymes with substitution. Substitution, good. So, by substitution, see sometimes you just need to write here. So, by substitution, okay, what are we substituting back into, guys?
2n into x.
Not just x, but
X to the 4th.
x to the 4th power, right, guys? Because we already know what x
2n
is,
to
right?
x, and x is to the 4th.
Okay, so we're going to say x to the 4th is equal to quantity 2n to the 4th. Okay, so we are substituting into x, and we're substituting into the statement x to the 4th power. Okay, so, and that's because that's what we're trying to operate on, right, guys? Okay, so that makes sense so far? All right. We need to show that this is even. Okay, suggestion as to what you guys might think to do next.
Expand.
Expand it. So instead of 2 to n to the 4th, what would you write that as?
16 to the n to the power 4th.
16 n to the 4th. And that's just by multiplication. Technically, it's the product of a power rule, but nobody cares what those rules are called, except for people that teach algebra. So this is just going to be by multiplication. How do I know, or what can I do to show that 16n to the 4th is even?
So take 2, then 8n to the power 4.
So we're going to factor it, right?
Yep.
16 is factored into 2 times 8, right? Now why not 4 times 4? Why not
Because
32 times a half?
Because you have to know the definition of 2n.
So we need to look for that definition of even. So twice 8n to the 4th, okay? That's just by factoring. And that's because we want to show that 16n to the 4th is even. To show something's even, it has to have a factor of 2. Nice. So this is going to be written by factorization, or we can just say factor. It's not a
GCF?
GCF, but you could just write factor, okay? If you write GCF, I'll just scratch it out and say factor. That doesn't
So
matter.
what's the difference between GCF and factor?
Greatest common factor means there's two terms.
Okay,
This is a singular term with
Term.
one factor, and you're only factoring out that coefficient.
Good.
Okay, does that make sense, Art?
Yeah.
Okay. Again, if you guys wrote it, I'm not that hard up on it. Okay. Guys, what do we know about 8n to the 4th?
that is equals to K.
Something integer, right? K. Okay, so by closure, this is going to be equal to 2k, and k is just not an even, but just any integer, right? Good. Even though this actually would be an even integer, since it's 8 times a number, okay, but we don't care about that. That's going to be k in z, okay? And guys, isn't it obvious, okay, this is a self-contained proof that no matter what number I plug in for k, we ended up with some sort of even integer, okay? So if I take any even integer, raise it to the 4th, I still get an even, okay? So, for step 3, we're going to say, thus, x to the 4th is equal to 2k and is even by the very definition, or you could just say by definition of. Okay. Step 3 is the easy part. You've gone through, you've done all the hard work, then you just got to tell everybody what it means. Okay. All right. So guys, those are two very basic proofs, okay? On a scale of 1 to 10 in this class, those are going to be about 1.5s, okay? So they will get more difficult, but I just wanted to start you guys out easy with this stuff. Okay? Questions about either proof, guys? Okay? Hopefully not too difficult, it's just new, okay? And just because something's new doesn't mean it's difficult. Okay. So, let's go ahead and try to take a look at another example, okay? Now, this one says that if I have some even integer, -1 to that even integer is 1, right? And you know this, right? Anytime you raise like -1 to the 16th power, it's +1. Now we get to prove that, okay? So let's go ahead and prove something like that. And again, the first thing that we have to do is we just have to define some variables, okay? So if I was to define a variable, or variables, let me ask you guys this first. How many variables do we need? One, because that's all we have in the problem, right? You guys are getting good at this, okay? So right away, let's let n be an element of z even, okay? And then in parentheses or brackets, sorry, n is arbitrary but particular. What's the only thing that we can say about n at this point? Or nothing. Yeah, we can say it's equal to 2m, 2k, 2p, 2 theta, whatever you want. Nice. Okay. So we're going to say that this is, by definition of even, we can say that n is equal to, you said 2m, correct? Okay, that's fine. Yeah, you never want to use a recursive definition with this. That would be kind of painful. So n is equal to 2m, and obviously m is going to be equal to an integer, or a set of integers. Okay, so that's easy enough, right guys? Alright, so that's step 1. We can all do that. We can define a variable, we can use the definition of that variable. Okay. Now we have to substitute. Okay? Now, all we're trying to do is we're trying to show that -1 to the n is equal to 1. Okay, so here's our substitution. So by substitution, okay, -1 to the n is equal to what, guys? -1 to the 2m. Sounds good. Nice, Mr. Weber. So -1 to the 2n. Okay. That doesn't hurt anybody's feelings. It might hurt your wrist because we have to write a lot, but such is life. Alright. Now, we need a few steps algebraically to show that that's actually equal to positive 1. Okay? And you guys might not know the names of the steps, but you might know the process. Okay? And that's what we're trying to fill in. So, if I was to ask you guys to show that that's equal to positive 1, somebody give me a suggestion.
Put them all on the same side and then factor.
Well, let's just focus on this right-hand side. But I like what you said about factoring. So, Don, did you have an idea? Oh, I see what you mean. You meant subtract this and then factor out like a -1 or something like that. Not a bad idea, okay? It won't help us in this instance, okay? But I like the idea of you seeing that common factor. So, did you have another suggestion, Don, or was that? That's okay. That's better than what I had. So, I'm just hoping you guys know what you're doing because I have no idea. So, another suggestion, maybe, guys? So, Paul.
we can do like -1 to the 2 times.
So, and Paul, would you mind terribly? I like your idea. I'm going to steal a little bit more out of that. I'm going to write it like this because I'm just that guy that likes to steal ideas. Okay? But I think he's right. In fact, I know he's right. Guys, isn't it true that you could factor off that m and just rewrite it like this? This is actually going backwards from something called the power of a product rule. We could just say factoring if you want to. That doesn't bother me. Okay? Seems like we use factoring a lot. So remember when you guys were at Algebra 1 and your teacher said, oh yeah, you got to learn how to factor. And you're like, when am I going to use this shit? And you're like, never. Well, we actually use it now. Okay? So this is by factoring. Okay, very nicely done, guys. All right. What's the next thing you guys might do at this point?
Square them.
Yeah, -1 squared is going to be 1, right guys?
Sure.
Last time I checked, that's basic computation. Nice. So by computation, this is equal to 1 to the m. Okay. Nobody doubts that, right guys? Okay. What do we know about 1 to any power?
It's equals to 1.
It always equals 1. It's a multiplicative identity, right guys? So if you want to write multiplicative identity, you can. If you just want to write by computation, that's fine too. Okay? So I'm going to be fancy about it because I got a master's degree. Might as well. Multiplicative, now I can't spell it. Multiplicative identity. And even if I could spell it right, you guys couldn't read my garbage up here. So, which is equal to 1. Okay? You could write computation, calculation, definition of 1 to any power. Okay, there's a lot of ways that you guys could justify this. All right. Guys, aren't we done? Haven't we shown that by the steps above, -1 to the n is equal to 1? Okay, so we've proved that whenever you raise -1 to an even power, it gives you positive 1. Okay, so we can say by above. Now there's no real definition that we've shown, right? So by above, we could just say -1 to the n is equal to 1 for all n in z even. Go away. See if you talk to it, it makes a difference. It's like when you're in an elevator and you're pushing the button a million times. That never works. Alright. So what we're seeing, guys, is sometimes we have to be a little bit sneaky with our algebra. Okay? For those of us that are suffering through Calc 2, we know that algebra is the bane of our existence, and trigonometry, and partial fraction decomposition, and Calc 2 in general. Regardless. Alright, questions I can answer about integer stuff, guys, so far? We haven't looked at perfect squares, so let's take a look at an example of something to where we have a perfect square. Okay? Go ahead, Ryan.
Would any of these problems have like existential?
Oh, I can't, if you do existential, you just prove it by existence. Okay? So it's really easy to show that. So, and we've already done the easy stuff. Now I'm making you guys suffer. That's okay, it's a valid question. Okay? So I'm not going to give those to you guys because they were just too easy. Okay? Alright, other questions, guys? Alright, so let's go ahead and do this one with a perfect square in it, okay? And then I'm going to let you guys practice one, just to make sure you guys get an opportunity to work through this. Okay, so for all x in the integers, okay, 5 quantity x squared plus 1 minus 4 quantity x squared plus x minus 1 is a perfect square, alright? Now, this seems really far-fetched, right, guys? So maybe we want to plug in a number to make sure it works. I mean, that couldn't hurt, okay? So let's just plug in a number, see if it works, okay? Let's plug in 0. Because 0 is a nice number to try, right? So this would be 5 times 1, which is 5, minus 0, minus 1. 5 minus 0 is 5, minus 1 is 4, which is a perfect square. Okay, so it works for 0. Let's see if it works for 1, just to see if it works. If I plug in a 1, 1 plus 1 is 2 times 5 is 10. 1 plus 1 is going to be 2 times 4, which is 8. 10 minus 8 is 4, is 2. 2 minus 1 is 1. 1 is a perfect square. So just by trying a couple of them, it looks like it works. Okay. Now I'm not saying sit there and try to find a counter example, because if it doesn't work, you probably try 1 or 2 and it doesn't work. All right. So we need one variable, right, guys? So let's let x be an element of z, not z even, not z odd, just z. Okay. X is arbitrary but particular. X is arbitrary but particular. Yawn. So really, there's nothing we can do with x, right? I mean, it's just even. It's not even, it's not odd. It just is what it is, okay? So literally, guys, this is step 1 right now. Well, that's not exciting. Because we don't have a definition for x, do we have a substitution step? No. So what do we do? Yeah, just go ahead and do the algebra, right? Let's just beat it up. We're going to factor, we're going to FOIL it out, right, guys? We're going to expand, okay? So we're going to say that by multiplication, this becomes 5x squared plus 5 minus 4x squared minus 4x minus 1. Okay? So all we did, guys, was we just did the distributive property